Hello. In this video on continuity, which is section 2.5 in your textbook, we're going to be looking at, well, continuity. And so a motivation for this section would be these two graphs. What would you say is different between these two graphs? One of them is a parabola and a straight line, and the other one is a parabola and a straight line. But it feels like there's something different between them. There's something fundamentally different about this one than this one. And if you start to look at it, you might use words like maybe connected. If you look at this graph, I would argue that it looks pretty connected. But if you look over at this graph, well, it doesn't quite seem as connected. I might even use a word like broken. This graph looks like it's got a break in it. It's got a broken part right here. And so we need to look at these two graphs and describe how one is connected, but the other one is broken. And what does that mean? What kind of words could we use? How could we talk about a math definition? Because maybe an English definition would say, well, it's connected. Maybe you'd say something like, you don't have to pick up your pencil to draw this one. But over for this one, you have to pick up your pencil. But again, it's more English. We need some type of math definition. And if we think about limits, well, as x approaches 2 from the left here, we'd have 4 as our limit. And as x approaches 2 from the right, we'd also have 4. But over here, as x approaches 2 from the left, we'd have 4. And here we'd probably have 3. If you were asked to find the limit as x approaches 2 on this one, you'd probably say the limit doesn't exist. And so this idea of the limit existing here and the limit not existing here can help motivate the definition for what this is. Now, we're not going to call this graph connected in this course. We're going to call it continuous, which is just a nicer mathematical word for this. And so the definition of a continuous function, or being continuous, visually it looks like the graph on the left, and mathematically a function is continuous at a number a if the limit as x approaches a of f of x equals f of a. Now, this portion should make sense. We have a limit, and you might have thought to say, well, the limit just has to exist. But technically, it has to also equal f of a, and in this statement, there's actually 3 criteria that are being listed. So remark, to check if a function is continuous at a, we actually have to check 3 things. The first thing we have to check is f of a defined? Because even if you had a limit from the left and right existing, back to our little example here, if these limits existed, but there was a hole over at 2, the graph still wouldn't be connected because there'd be a hole in it. So the first thing you have to have is the function has to be defined at a. Then, of course, you have to check, does the limit exist, which usually requires checking the left and right limit. And then the third thing you have to check, which is a bit of a technicality, but it's still required, is does the limit equal the function at a? So we're going to look at how each one of these 3 could fail. So for the first one here, for number 1, f of a could not be defined. So that might look something like this. You got a little curve, you got a hole, and then it keeps going. For here, f of a, if that hole is at a, f of a is undefined. Undefined. Now for number 2 to fail, this would be where you have the limit from the left and the right being different. So maybe you've got some graph that goes like this, and then continues on like this. Here, the limit as x approaches a of f of x does not exist. And for number 3, you have that weird situation where you have a limit existing, but instead of it being nice and connected, there's a hole. And for some reason, the hole is filled in above or below for some reason. This is where you have a limit existing, limit x approaches a of f of x, but for some reason it doesn't equal f of a. We've decided to fill the hole in the wrong place. And so we'll look at some examples of continuous functions and functions that are not continuous and how we determine which is which. Now, as a further definition, a function f is continuous on an open interval ab if it's continuous at every number in the interval a to b. Now, initially, this might seem overwhelming. There's an infinite number of numbers between a and b, and we have to check a whole lot of points. But we don't actually have to, because there's going to be some theorems that help us determine which functions are continuous, which ones aren't, and which ones are continuous in large portions of their domain. So the first theorem we'll look at here is every polynomial function is continuous over its domain. So we're going to prove it for degree 2. So let's take f of x equal to c2 x to 2 c1x plus c0. Now let's look at those three conditions. Step 1. What is f of a? Well, it'll be c2a squared c1a plus c0. All right, step 2. What's the limit as x approaches a of f of x? Well, hopefully we remember our limit laws. The limit of a polynomial is actually the polynomial evaluated at a. So it's c2a squared plus c1a plus c0. This is limit law number 9. So, step 3, are these two equal? Was f of a equal to the limit? Well, of course it is. So, step 3, the limit as x approaches a of f of x equals f of a, and we're done. Therefore, fx is continuous at x equals to a. And since it's continuous at a could be any point, so it's continuous over the whole domain. Now, you probably could have argued this just from reason. If you think about drawing a polynomial, are polynomials connected? Do you have to pick up your pencil when you're drawing a polynomial? Of course not. Polynomials are nice, wonderful functions that are perfectly connected, and so of course they would be continuous. Now, we're not going to prove this, but as a remark, the following types of functions are also continuous at every number in their domains. So polynomial functions, which we just proved, but also rational functions. If you imagine a rational function, right, sometimes we think for the rational functions, a classic example would be your swoosh graph, 1 over x. And in this case, of course, it's going to be continuous. It's not going to be continuous at certain locations, which we'll look at, but everywhere it's defined, you're going to be able to draw it, no big deal. How about root functions, square roots? Well, yeah, those are going to be continuous. Trig functions, I mean, those are, of course, continuous. They just go on and on and on. Exponential functions, logarithmic functions, absolute value functions, all these functions that we know and love from pre-cal are all going to be continuous on their domains. Additionally, if you have two functions, fx and gx, that are both continuous at a point x, then f plus g, f minus g, f times g, and f divided by g are also all continuous. So you could add two continuous functions and get another continuous function, or subtract them, multiply them, or divide them. There's no proof for this theorem, but I'll just sketch the proof anyway so you can see what it looks like. If you were to do, let's say, f plus g, well, let's do that one. For number 1, f of f plus g of a would be f of a plus g of a. That's how we do addition when we look at functions. If you're going to do f plus g of a, you just do f of a and you add g of a. Now, if you're going to do the limit as x approaches a of f of x plus g of x, well, remember we have a limit law. Limit law 3 allows us to add the limits. So this becomes plus between the two limits. Limit x approaches a of fx plus limit x approaches a of g of x. And this is limit law 3. Well, f of x is continuous and g of x is continuous, so limit x approaches a of f of x is just f of a. Limit x approaches a of g of x is also g of a. And then for number 3, well, clearly this and this, they're both equal because they're f of a plus g of a, f of a plus g of a. And so here, limit x approaches a of fx plus g of x is equal to f plus g of A. So that actually would be a complete proof there. You don't need to know the proofs of these ones, but it's nice to see the limit laws in action. So let's go ahead and find the interval where f of x is continuous. So here's our function. And what we're going to do is look for where it's defined, because this is a rational function. So it should be continuous on the whole domain, wherever it is defined. So let's go ahead and try to find the domain. Okay, well, we know for rational functions, domain issues come from the denominator. So we should factor. So factor x squared minus 7x plus 12. Looks like that's going to be x minus 3 and x minus 4. So therefore, x could not be equal to 3 and x could not be equal to 4. Because if x was equal to 3 or 4, then that would make the denominator 0. Which means the domain is all the real numbers except for 3 and 4. So negative infinity to 3, union 3 to 4, union 4 to infinity. All right, well that's the domain. And so therefore, fx is continuous on minus infinity to 3, union 3 to 4, union 4 to infinity. All right, let's go ahead and find the interval where this function is continuous. Again, we need to find the domain, and there's actually 3 functions. There's this one, and this one. So we're going to find the domain of each function on its own. So let's do root x domain. Hopefully you remember from pre-cal, for square root function, it's defined for all positive numbers and 0. All right, x plus 1 over x minus 1 domain. Well, this one's a little trickier. We just can't have x equal to 1. So this is negative infinity to 1, union 1 to infinity. And then x over x squared plus 2. Remember, we actually can't factor a sum of squares. So this does not factor, which means it's got domain, all real numbers, negative infinity to infinity. Now, where is the overall function defined? If these are the 3 portions, the overall function is defined where all 3 of these overlap. So we need to think a little critically, where are all 3 of these being defined? Where is the overlap of these 3 domains? Well, certainly not any negative numbers because of the first portion, so it's got to start at 0. So if we were going to write down here, the domain of fx, certainly it's got to start at 0. And then we can't include the number 1 because of that second domain. But everything else is good to go. So that's going to be the domain of fx. And so therefore, fx is continuous on 0 to 1, union 1 to infinity. Now just for fun, we're going to go ahead and look at this function on Desmos. So here's the function, pretty interesting looking function. It's clearly got a nice continuous connected portion here. Then it's not defined at x equals to 1, so it's not continuous there. But then here again, it's a nice connected graph. And so this function is continuous everywhere from 0 to 1, and then from 1 all the way to infinity. Again, there's no other places where the graph would be broken. This is the one place at x equals to 1 where there is a break in the graph. Now let's go ahead and look at a more complicated function. Here we have fx, and it's going to be a piecewise function, so it comes in pieces. There's going to be 3 when x is less than or equal to 0, 3 minus x squared when x is between 0 and 2, and negative 1 when x is greater than or equal to 2. We want to show this is continuous on negative infinity to infinity. Well, how might we do that? How might we show that it's continuous? And we're going to look at each piece on its own. This is a straight line at 3. Technically, it's actually a polynomial of degree 0, but you can think of it as a horizontal line. Are horizontal lines connected? Are they continuous? Certainly they are. And over here, we have another horizontal line. That's going to be connected, no big deal. Over here in the middle, we have a parabola. Parabolas are polynomials, they're connected, no big deal. But if we notice, this whole function does have a bit of a interesting twist because it's piecewise. And so it's going to be a line and a parabola and another line. And you could imagine what happens if this line doesn't connect with this parabola, right? Just like we had on our very first example, what if the parabola and the line don't line up? We might have a break. And in particular, we might have a break here at x equals to 0, or here at x equals to 2. These are the potential problems. Potential problems. They might not be problems. In fact, we're supposed to show that they're not, but they might be problems, and that's where we're going to investigate. So we're going to start with x equals to 0. To do this, we're going to look at the 3 steps. So first part, what is f of 0? Well, f of 0 is equal to, when x is less than or equal to 0, it's 3, so it's strictly 3. All right, 2, we're going to look at the limit x approaches 0 from the left. When we go from the left of fx, that means we're going for values less than 0, which means we're doing 3. The limit of 3, of course, is 3. Then we'll do the limit as x approaches 0 from the right of fx. It means we're taking values greater than 0. So that means we're going to look at the 3 minus x squared. So that gives you 3 minus 0 squared, which is 3. These, of course, are equal. So we could say, therefore, the limit as x approaches 0 over all of fx is equal to 3. And then, of course, we need step number 3. Limit x approaches 0 of f of x, it's 3, which is also equal to f of 0. So we're good to go. Therefore, fx is continuous at x equal to 0. Now I encourage you to pause the video and give it a try for 2. Have x equal to 2 and go through the same steps. See if you can show that the function is continuous at x equals to 2. All right, assuming you gave it a try, let's go ahead and write down the steps here. So now we're going to do x equal to 2, and we go through the same 3 steps. So step 1, we find f of 2. When x is equal to 2, apparently it's negative 1. Then we do the limit x approaches 2 from the left of fx. Means we're taking values less than 2. So that means we're going to look at 3 minus x squared. That's going to give you 3 minus 4, which is negative 1. Next up, we look at x approaching 2 from the right of fx, which is going to be the limit x approaches 2. If we're doing values greater than 2, it's going to be negative 1. The limit of negative 1 is equal to just negative 1 because it's a constant, and these are equal. So therefore, the limit x approaches 2 over all of fx must be equal to negative 1. And of course, the number we got here, negative 1, is the same as the number we started with. So the limit x approaches to 2 of fx equals f of 2. Therefore, fx is continuous at x equal to 2. And now we should add a concluding statement. Something like, since fx is made of 3 polynomial functions, which are continuous, on their domains fx is continuous on negative infinity to infinity. So we've shown it's continuous on the whole real number line. Now it's very satisfying to look at this graph on Desmos. We can see here the nice, wonderful horizontal line, the parabola, and the other horizontal line. And you can see that these graphs beautifully line up with one another, so the overall graph is definitely continuous. You can draw it without picking up your pencil. It's connected, and it looks, I think, very beautiful. Now let's try some multiple choice questions. For starters, where is the function secant x discontinuous? At 0, pi by 2, pi, or 2 pi? Go ahead and pause the video and give it a try. All right, well, hopefully you remember the domain of secant. Because secant is 1 over cosine, if cosine of x is equal to 0, that would be bad because you'd have a 0 in the bottom. And that happens when x is equal to pi by 2. So if x is pi by 2, cos is 0. If cos of 0, 1 over 0 is undefined, which means secant is undefined. And if secant is undefined, then it's definitely discontinuous. So the answer is B. Determine the number where f of x is discontinuous. All right, this one's a little more interesting. We have x less than or equal to 1 and x greater than 1. So hypothetically, this would be where the issue would happen. It's possible that at x equal to 1, there's an issue. And if you do the limit on the left-hand side, as x approaches 1 from the left, you're plugging it into 3x plus 2, which gives you 3 plus 2, which is 5. But when you do the limit on the right-hand side, you get 0. And 5 and 0 are not equal to each other. So the issue indeed is x equal to 1. The function is discontinuous there. So let's go ahead and try a couple more continuity examples before we finish the video. Let's discuss the continuity of fx, where fx is either 2x plus 1 when x is less than 0, or x squared when x is greater than or equal to 0. And so again, the potential issue is at x equals to 0, and I tend to think of this like a handoff if you were playing a sport in football or rugby. What you have here is one function running along, and then at x equals to 0, it hands off to the other function, x squared. And the question is the handoff successful? Right here, does the one portion hand off properly to the other function, or is there a break? Do they miss each other? Is there some type of issue there? So let's see what happens. We're going to check x equals to 0. So step 1, of course, is to find f of 0, which means we use the bottom portion, so 0 squared, which is 0. Number 2 would be to find the limit. Limit x approaches 0 from the left. Well, that's going to be looking at 2x plus 1. So we get 2 times 0 plus 1, which is going to be 1. Limit x approaches 0 from the right. In this case, we're going to look at the portion greater than 0, so that's x squared. 0 squared is 0. Uh-oh. These are not equal. Well, they're not equal, so therefore the limit as x approaches 0 of f of x does not exist. And so we don't have to continue on to step 3. We don't have to see if the limit is equal to the function because the limit doesn't even exist. We've already failed. And so therefore the function is not continuous at 0. Therefore fx is not continuous at x equals to 0. But it is continuous on the rest, because this is a polynomial and this is a polynomial. So it is continuous on the rest of the real number line, just not at 0. So we'll say since 2x plus 1 and x squared are both polynomials, fx is continuous so are both polynomials, and maybe we should add and continuous. Fx is continuous on negative infinity to 0, union 0 to infinity. And we'll take a look at this on Desmos. So here you can really clearly see the one side gives us a limit of 1, the other side gives us a limit of 0, and because of that, we have the limit not existing, and we have this break in the graphs. Of course, on this portion, it's all continuous, and on this portion, it's all continuous, but right at x equals to 0, it is not continuous. Sometimes we use the word discontinuous. So let's go ahead and look at another example here. Again, we have a function that's defined in 3 pieces. We've got 3, we've got x plus 6, and we've got 2x squared plus 2x plus 2. In this portion, it's between negative 10 and negative 3. Here, negative 3 and 0, and here, greater than or equal to 0. So we're going to discuss the continuity on negative 10 to infinity. Now again, because these are polynomials, they're clearly going to be continuous on their domains, but the issue is going to be at negative 3 and potentially at 0, because that's where we hand off from one function to the other. So let's go ahead and check x equal to negative 3. So if we begin to investigate this, well, we'll start with step 1, 2, and 3. So for step 1, we have x equal to negative 3. We want to find f of negative 3. That means we use the top portion, which is just 3. For step 2, we do the limit x approaches negative 3 from the left of fx, which means we're doing x approaches negative 3 from the left of the number 3, which is just 3. We do the limit x approaches negative 3 from the right of fx, which means we're going to do the limit x approaches negative 3 from the right. It's going to be x plus 6, which plugs in as negative 3 plus 6, which is also 3. These are equal. So the limit x approaches negative 3 of fx overall, it definitely exists and it equals 3. And for the last step, clearly 3 and 3 are the same. So since the limit of the function equals the function at negative 3, therefore fx is continuous at x equal to negative 3. All right, we need to also check x equal to 0. So go ahead and pause the video and try x equals to 0. So I'm assuming you gave that a shot. Let's do that over here. X equal to 0. So step 1, f of 0 is going to be equal to, well, it's equal to 0, we use the bottom portion. So you get 2 times 0 squared plus 2 times 0 plus 2, so just 2. Then limit x approaches 0 from the left. That means we're going to use the x plus 6 portion. So x approaches 0 from the left of x plus 6, which is going to give us 6. Then we do the limit x approaches 0 from the right, which means we do that 2x squared, etc. portion. 2x squared plus 2x plus 2, which just gives you 2. And these, of course, are not equal. Not equal. So that means, therefore, the limit as x approaches 0 of fx does not exist. And so we don't even have to check number 3. Unfortunately, this means that fx is not continuous at x equal to 0. So it failed to be continuous there. But we'll go ahead and mention our conclusion. Since 3 and x plus 6 and 2x squared plus 2x plus 2 are polynomials, which are continuous, f of x is continuous, on the rest of it. So negative 10 to 0, union 0 to infinity. So for homework, you can go ahead and try some textbook questions. In particular, on page 24, you can try 3A, 4 to 8, 11 to 14, 7 to 22, 33, and 34. And as always, thanks for watching.